Welcome to everybody on Zoom. We are going to have a shorter session than planned. I had a guest speaker planned to present on LiDAR and potentially do a demo, but they were unable to attend. There's a company called Rock Robotics that makes a really good UAS LiDAR system. I'm going to show some of their data. The CEO of the company, Harrison Knoll, was hoping to come but was unable to. Has anybody ever seen Harrison's YouTube channel? He goes by Indiana Drones. He's a really high energy, good speaker. He loves what he's doing, and he's the CEO of the company. So I'm going to show you some of the data from his system later, but he's not here today. So we'll probably end. We'll probably only go half an hour or so like that, and we'll end the day early. I know it's been a long day anyway, so well, it's been a long day for me anyway. Okay. Okay. We'll see how long-winded I get. I'll often say that I'm only going to talk for a little while and then yam. So, okay. So UAS LiDAR. We've been talking a lot about all the great 2.5 and 3D products that we can generate using photogrammetry, and how great it is that a simple system like a camera with a bunch of overlapping photos can end up giving you not only a nice seamless orthorectified photo, but a surface model as well. And that's a passive sensing system, right? The camera is just taking pictures based on reflected light, light that came from the sun. And we create a surface model that is a model of the upper surface of everything we're seeing, right? So we're seeing the tops of trees and things like that, and we're not seeing down through porous surfaces and things. So LiDAR is a method for actively sensing, and we'll talk about how it works and all that as we go. So the name LiDAR came from the same it's the same kind of acronym as radar and sonar, but in this case, the energy that's being emitted by the active sensor is light. So it stands for light detection and ranging. It was first developed in the 60s for satellite tracking, but the first on land use was this kind of wicked looking thing, the Co-LiDAR Mark II rangefinder, which was used for artillery ranging. It was a military application, of course. So a lot of the technology we use, GPS and other stuff, starts out as some kind of war-related thing, and then ends up having a much better peacetime use. So again, it's an active remote sensing technology. We've got something that sends out a pulse, and it bounces back to us, and we measure the elapsed time, and we get the distance, right? So if we know how fast light travels, which we know pretty well, and we know that anything that bounces back, we know that anything that came back to us had to go there and come back. So we've got the two-way travel time. So if we cut that in half and we divide by the speed of light, then we know, and we multiply by the speed of light, then we know how far away the thing was. There's different wavelengths that are used depending on the medium that something needs to go, that the light needs to go through. Bathymetric LiDAR needs to penetrate through water, so we use different wavelengths than we use terrestrially. But the point is that we're shooting out light and waiting for it to come back. And of course, light's fast, right? It comes back pretty quick. So you got to have a pretty good clock. You got to be able to tell the time difference is very, very, very small, even for long distances. So the basic concept here is that we've got a laser and we've got a way to sweep it across our scene. That can be a spinning mirror, it can be some kind of solid state thing, but in general, the idea is that the laser's shooting out and it's not just going once, it's going across the whole scene. It's pulsing many, many, many times very quickly across the whole scene. And as it comes back, we build a model of the points it reflected off of based on the travel time. And of course, if we have an obstacle, then we get a shadow behind it, right? So we're sweeping the light pulses across the scene and getting point measurements. Every time the light bounces off of something and comes back, we get a point there. And we get it off of generally the first solid object, but in some cases where we have situations like foliage or tree canopy, we can get in between the leaves and stuff, and we can get reflections from the ground as well as the canopy. So we're moving that sweep across the scene, but we're also moving the laser across the landscape. And so what we're basically doing is building, I don't know if you can see this. Can we dim the lights just a little bit? What we're doing is we're building a swath as we go. The laser is on an aircraft in this situation, a crewed aircraft. And as we move it across the landscape, we get a strip of XYZ measurements across our swath. It's just like the same way a multi-beam sonar would work. In order to make sense of those numbers, we have to know the attitude of the aircraft and the sensor very precisely. We need an inertial motion unit, an IMU, which you have in your drone, but we need a really, really good one because the laser is scanning at a very, very high update rate. And so we need to know the attitude of the aircraft. That is its pitch, roll, and yaw. You know all those numbers from, or those names from talking about other uncrewed aircraft, as well as its position in XY space and some other factors. We need to know all those very, very, very quickly, like 200 hertz. We need to know it 200 times a second, and to very, very small hundredths of degrees. And those systems are kind of expensive. So the parts of a LiDAR system are this IMU and the GNSS together are kind of usually called the inertial navigation system. So another acronym, INS. It's made up of your high precision RTK GNSS, a 6 degree of freedom inertial motion unit. That is 6 degrees, includes all of these roll, pitch, yaw, which direction you're facing, heave, up and down. So we need to be able to measure all those things very, very quickly to hundredths of a degree. And amazingly, though, the sensors that can do that, like this Aplanix ep30, have gotten really small. Some of these systems that can do this are actually classified as munitions because they're the same kind of thing you would put in a cruise missile to make sure it got to its target. And so there are sometimes some ITAR, if you're a US citizen, some ITAR or other customs limitations on taking some of these systems out of the country. So you've got your GNSS, you've got your INS, and then you've got a sensor. And the ones that are small enough to go on drones are always evolving, getting smaller, cheaper, better. Common ones that are used on drone systems are these puck style LiDAR, made by, most popular one is made by a company called Velodyne. And then the other one that's popular, I'm gonna move that thing out of the way, is the LiveOx. It looks more like a little TV. In fact, the DJI L1 LiDAR is based on a LiveOx sensor. There's some larger and better systems. Regal is a German company that's been making LiDAR, terrestrial scanning LiDAR, as well as aerial LiDAR for many, many years. And one of their best units is this Minibus. We're talking, well, we'll get there. The Rock Robotics system that you see here is based on a LiveOx sensor. It also has an RGB camera attached to it. This is last year's talk. It's $20K now. Whoops, It's a smart board. So I can't touch the whiteboard or otherwise it thinks I'm clicking. The DJI Zenmuse L1 again is down here. That can go on the M300 only. So it's a DJI specific LiDAR and cannot go on any of their earlier drones, only on the M300. This is the Yellow Scan Surveyor. This is the TrueView system. It's based on the Minibucks. You see, they're all different sizes. This can go on something as small as an M300. This is, you got to have an M600 or bigger to carry this. And the applications for fixed wings, of course, don't usually involve gimbals, but they can go on fixed wings as well. There's more and more all the time, and new ones are coming up, and then the companies are folding, and so it's a volatile, it's a fluid market for sure. But again, you can spend anywhere from say $15,000 or $20,000 at the low end to a couple $100,000 on just the LiDAR itself. No drone, no nothing else. Most of these incorporate the INS part of it, at least with them. So here's a picture of, just to give you an idea of scale. This is a DJI M300, and that's the Rock Robotics R2A mounted underneath it. Here's a TrueView mounted on a M600. You see the legs are folded up, and they've got a bunch of other well on there, but yeah, a TrueView system, a system that size needs a heavy lifter to get it up in the air. So if you're interested in sticking your toes in the LiDAR water, then you want to think about when you're shopping around, the parameters that are important for a LiDAR system. And this is for any LiDAR system, but it all applies to UAS as well as other places. So these are some of the numbers that they will give you, the vendors will, or developers will give you. And that is the scan rate. That is how many times does it scan per second? Because obviously that's going to affect your data density, right? Given a constant rate of travel, of course, if you stay put and you scan, you're just getting the same place over and over again. But given any kind of constant rate of travel, the faster you're scanning, the more points you get, the denser they are along track for your speed of travel. The scan coverage is the field of view, or the angular coverage. If it's got a really narrow angular coverage and you want to do lots of lines that have at least a little bit of overlap between them, you're doing more lines, right? You got wider coverage and the data are actually good all the way out to the edges of the coverage, then you can do fewer lines. These lasers aren't super powerful, so they usually have some kind of range limitation. Your LiDAR system might only work up to 100 meters altitude, or it might be good to, 200 or whatever. Of course, if you're working within Part 107 limitations, you can only go 400 feet. That's 120 meters. So, so you may not need a LiDAR that can go farther than that. But there's the operating altitude range. But what they also won't tell you a lot of the time is whether that takes into account the field of view, and whether that's based on the altitude to which you can still get good data out at the edges, because it's going farther out at the edges than it is at nadir, right? So you want to ask these questions if you're shopping. The number of returns is important too, and I don't know if that's on this page. Yeah. Oops. No. Well, this is just a note to say, even whatever they tell you, it's probably better than reality, right? So if they say, oh, our LiDAR does this and this and this, and it's probably not quite that good. Just like when DJI tells you, oh, you're going to get 35 minutes of flight time on this battery. Well, no, you're not. But you can at least have something to go by. How good the INS is, what the wavelength of the laser, what its environmental tolerances are. I mean, one of the things that's great about LiDAR is it's an active system, right? So we can sample at night. We don't need sunlight to take measurements, take XYZ measurements of of our study area. All these things. How heavy is it? What kind of aircraft can I put it on? How do you calibrate it? So a lot of LiDAR have calibration sequences or calibration methods that involve you doing figure eights or lines in certain orientations to each other so that the LiDAR sensor itself and the INS can be married up. The data can be joined up in a way that doesn't give you artifacts. And so some systems are really, really simple and fast to calibrate, and some are not so much. So those are also things you want to find out before you spend lots and lots of money on a LiDAR system. You want to see samples of data. You want to know what kind of support you're going to get. And of course, in some cases, you care where it was made. And that can be just enough. That can affect support even. If you're buying from a company that's on the other side of the planet and they don't have a local support desk, then you may be 8 hours out from them and you may be waiting in the field while you thought you were going to be surveying for an answer from their support because they're sleeping. So to process the data, there are various softwares. Some of them are cloud-based, some of them are local. There's usually a bunch of steps involved. The first thing that you usually end up doing is taking the trajectory data, that is the INS data, the GNSS or the position and attitude data, and running it through a process to generate what we call a trajectory. It's basically where the sensor went and how it was pointed. That's separate from the range data that you got from the LiDAR. You then merge the trajectory with, so this is the process of generating the trajectory, often done in a piece of software, something like PosPack from Planix. I don't know if anybody's ever seen this before, but this is using a virtual reference system of base stations around where the study site was. It's PPK, basically. You then merge that trajectory with the LiDAR data, and that's where you get your first real point cloud. That's where you've got XYZ points, but it's going to be full of noise. There's going to be lots and lots of stray XYZ points that aren't real. They don't really represent objects that the light bounced off of, or they may represent an object that the light bounced off of, but not the one you care about, like a bird or little rain droplets, or lots and lots of things can give you spurious XYZ points. And there's always going to be a process of cleaning out the noise. That can be manual or automated, or a combination of both. Almost always you end up taking a mouse and circling stuff that you want to reject. And almost all software that has you doing that doesn't delete those points. They just get flagged as rejected and ignored from then on, but you could bring them back if you wanted to. If you realized, oh, wait, that was a mistake, that's real, I'll bring it back. After you've cleaned it, often there's a step of classifying the points. So assigning some kind of categorical flag or attribute to them to indicate what they are: a building, bare ground, tree, power line, whatever. That's real useful in analysis later, but it can also be real useful for filtering. If we want to get rid of all the buildings and just see the bare earth model, and we have the points are all classified, we can do that. And then generally, we're going to export and use the data somewhere else, GIS, CAD, somewhere. So here's an example of a classified data set where these yellow stripes, touch it again, these yellow stripes and these purple stripes that you can't see very well are power lines. And this is a building. And obviously those are trees and that's background. So why do you use LiDAR? Why do you use photogrammetry? Which one's better? It depends. pros and cons to each. Definitely a pro of structure from motion and photogrammetry is that it's cheaper, it's easier. There's a lot less involved. It's not like cakewalk, as you saw, as you're continuing to see, but it's a lot easier and a lot lower cost to get into. On the downside, you get a surface model only. You get a model of what the top thing was that the light bounced off of that ended up in the image, right? The processing times actually for photogrammetry are often longer than the processing times for LiDAR. And the point cloud that we end up with is indirectly measured. It's not, it's a guess. Whereas with LiDAR, all the opposite of those things. And this one, these two are actually the first three are biggies, because the ability to not worry about ambient light in terms of when we can survey opens up a bigger window of when it's doable. Now, like heavy rain or really, really dense fog or something like that is still going to shut us down, but darkness or twilight or something like that is no big deal. And the multiple returns. I know I have a slide in here that shows this. There we go. So the multiple returns is a big deal. Depending on the LiDAR system, it may be able to get only one return, which means, so if we look at this, this is a time series right here. This is the reflected light coming back from a single pulse. And the first thing that the light bounces off of is going to give us our first return. And that time is shorter, so that distance was shorter. And then if some of the light gets past there and bounces off of something else and gives us a strong enough return, we're going to get a second one. And all the way, and we may be able to get 3 or 5 or something returns. And so we may be able to get the ground and some understory vegetation and different places in the canopy, and then the very top of the canopy. So if we get multiple returns, we're able to get more Z points per pulse, and we're able to model things like canopy structure, overhangs, things like that. We're able to classify the data then as tree versus bare earth, and we can quantify how many trees we have. We can get rid of the trees or leave them in and do all kinds of great stuff. So whereas a photogrammetric surface model would give us the ground and then a big bump is the tree. Yes.
Just to elaborate, sorry, you're saying the one pulse is going to give you multiple data outputs in the network?
If not one pulse, we're pinging very, very, very fast. But this is the single pulse, what we're talking about here. So you get it both ways. You get it by pinging so fast or by pulsing so fast that you're shooting in between things. But you're also getting on a single pulse, there's backscatter, right? You get some of it back when you hit something, but some of it keeps going. And I mean, obviously, if it's a mirror or something like that, you're not going to get anything behind it, or if it's a rock. But if it's something that is not entirely solid, you can get multiple returns back. And so, but that's a limitation of the system itself. A given LiDAR may only be able to record one return, or it may be able to record 3 returns. And doing so can sometimes affect, well, it's going to affect your data rate for sure, right? Because if you're getting 3 Z measurements instead of 1 every time, you're or potentially 3, you're not always going to get, I mean, over here, we're getting a single return, right? We're just getting the ground. There's nothing to see in between, and we're getting the ground, and that's it. The first return is the last return in that case. But anywhere else, if we're getting more Z points per pulse, then our data volume is going way up. The data processing is going to be higher. So it comes with a cost, but it gives a lot of additional information. In some cases, we can distinguish species by, you know, how opaque they are to the laser pulses. We can sometimes use it to gauge condition or health. Anyway, multiple returns is a good thing. It's an advantage of LiDAR over photogrammetry. Question? Yes, so we know very precisely the position of the aircraft in 3 dimensions, as well as its attitude. So that INS system is giving us the height of the aircraft, the XY position of the aircraft, and exactly how the aircraft is pointed in 6 degrees of freedom. Also, if the aircraft is going like this, like turbulence, then that's being measured as well. So yes, that's crucial. So data products you get out. Obviously, you're going to get a classified point cloud, and that can be in a bunch of different formats, LAS, XYZ. We can get, if we have a camera on the system that's calibrated with the LiDAR, we can get an RGB color for each point in the XYZ point cloud. So we can actually create almost a photo mosaic from colorizing the points if they're dense enough. We can see what the ground cover is and other things like that, because we've got just like a pixel. Every point is a pixel basically, right? Because we've got RGB color for every XYZ point. We can get a digital surface model. We can get a digital terrain model by removing the stuff that's not the ground. If we have multiple returns, especially. We can get 3D meshes, orthomosaics. So we get all the products that we get normally from photogrammetry plus a few. So let's see if this works. This is one of Indiana Drones' little YouTube videos. I don't think he's actually on it, but what it is he went to Six Flags St. Louis, and there's this giant wood roller coaster called the Boss, right? And it's a wood roller coaster, so it's all this really, really intricate wood structure with cross bracing and this lattices. It's crazy in terms of, it's very complex, right? So if we did a photogrammetric study of this, we'd get this smooth shape, right? It wouldn't look, the photo would look like that, but the 3D model, the 2.5D model, would not look like that. So let's see if I can get, oh wait, that's not it. Back up. That's my last. Let me back up. There should be, oh, you know what? I did it with a link last time. That's too bad. I'm gonna have to, yeah, let's see if I can, how much time I got? Oh, I got lots of time. Bear with me here, please. Okay. Sorry, I shouldn't have to do this. Yes, there it is. Okay. Yeah, that's a great question. That's a great question. I'll go back to this tab in a minute. Chat. Okay, so Drew's asking, is the light energy emitted by these smaller LiDAR units hazardous to the human eye? And the answer is no, they're eye safe. I mean, I wouldn't stare into one. It wouldn't be a good idea, but they're the wavelengths and the pulse energy are intended to be eye safe. So you don't have to, for example, make sure you clear every, I mean, other than the Part 107 regulations, in terms of the LiDAR safety, you don't have to make sure that there's no one in your survey area or animals aren't going to be at risk. They are all eye safe. So if there's no other questions, let's see if I can get this to maximize. I wish I could. Well, this may be the best I can do on the fly. But what you're seeing here, it's transitioning between the RGB colored point cloud and a point cloud that's colored by elevation. But this was flown in, and I can show you offline. Actually, let's see what happens if we do this. So last time I gave this talk, I was all prepared, and this time I was giving a breakout group before this, so that's my excuse anyway. No, we don't want that. Let's see if we can go 3D. So this is the point cloud. It's filling in kind of slowly. It looks not so dense as we're waiting for it to fill in. But if we do zoom in, we give it a minute to draw. You'll see that that lattice work structure of the roller coaster was really captured. I hope it doesn't take too long. We can also see, it's giving us the controls to color it by. So he did this. There we go. He did this in. He didn't do a. What's the word from today? When we do a mow the lawn. I quit. I'm out. Boostrophodonic. The mow the lawn pattern, right? So he didn't do that for this survey. He just flew the drone around. He did like a couple passes, went around it. If I'm fast enough at figuring out the interface here, since I haven't looked at it in a while, I can have it show the track lines. Let me see here. There is a way for me to, I can make this color. Right now it's coloring. Let me zoom out so you can see it a little better. So I was zoomed in maybe a little bit too much. Right now it's colored by elevation, right? So blue is low and the warmer colors are higher, right? But we can also, we don't want to edit. We don't want to measure. There we go. That's what we want. We can do it by RGB. So there's our picture, right? We can do it by GPS time. So that's going to show us the order in which those points were recorded, right? So in this case, I think red is going to be more recent and blue is going to be older. So this is kind of shows you how many passes he did in areas where there's lots of different colors, like up here. He went over that a bunch of times, right? There's some really early pings and then some really late ones. Over here, it's only really late, I guess. So looking at it in terms of time tells us the order in which things were recorded. Here's a return number. So now the reds are the first returns and the cool colors are the last returns. I think the Rock Robotic does, it's either 3 or 5. I'm sorry, I don't remember. Let's do, I don't know if this is classified or not. No. So this is an unclassified data set. So when we tell it to colorize by classification, nothing's been labeled as structure versus ground versus vegetation or everything. It's all coming up gray. So someone would have to go in and tell the system what the different materials were, what the different objects were. Jeff, did you have a question? Good question. There's a camera that's aligned with the sensor, and the camera is taking pictures at a much slower sample rate. So it might be only taking pictures, you know, every couple seconds, but then the RGB color of the same place on the ground as the XYZ point came from is assigned. So the RGB pixel value is, so then you end up with every pixel having a color. Again, this is a point cloud, so at some levels of zoom, it looks like an actual surface model, but it's really just lots and lots. It's a very dense point cloud. Question? Yes. Yes, as a matter of fact, even photogrammetry software can export a 3D mesh, an OBJ file, or which can be turned into an STL and can be 3D printed really easily. So yeah, 3D meshes are common outputs of both systems, both photogrammetric and so I think I'm going to finish with looking at this. I don't think there's anything more that we can really glean from this, but then the last thing I have to show you is go back to the slideshow. This is another short video from Rock's website, and what I think is cool is that it transitions from the different classifications and different products that you get out of this, and it shows data density, how well forest canopy, but also the ground in between the trees can be recorded. Here we are looking at it by elevation. There's it's gonna, I think, transition to another area where we're gonna see some different data. But of course, these are promotional. They took the best stuff they had and they were careful to edit it to show the stuff that looks really good. But here's some great examples of a ruined piece of highway and all the girders and things that are all broken and bent. And we're seeing underneath stuff, right? We're getting true three-dimensional here, not 2.5 dimensional. We're getting a three-dimensional model, not just a surface model with one Z at any given XY. Here's some power lines. Now they've been classified. They're different color. Anyway, LiDAR's really cool stuff. It's really expensive. It's got a pretty steep learning curve, but it's a very powerful tool. And the technology is really emerging quickly to the point where it's getting more and more affordable and simpler in terms of the entry level sort of learning curve involved. So I like LiDAR. I'll take any questions you have, and then we'll, as I said, end a little bit early, and maybe Sean will want to present something. But any more questions about LiDAR? Yes, as a matter of fact, when I went to Rock Robotics website and went to their, so Rock Robotic sells the LiDAR, but they also have a thing called the Rock Cloud, which is a processing tool, a cloud tool, which they charge you more money for, obviously. But you can get a free trial account, and you can also get to some of their data products online and download them. There's also lots of LiDAR data available from USGS and other government agencies. It's not all kind of as cool as the roller coaster, but yeah, there's lots of publicly available LiDAR data you can play with. If I understand right, so in my previous life, when I was doing the seafloor mapping stuff, We have, and we still have it. We don't use it. There's no one to use it anymore. We have a terrestrial scanning LiDAR system. So it's intended not to shoot down from an aircraft, but to shoot out across the landscape. And we put it on a boat and then traveled along the coastline, aiming it inshore. And as a matter of fact, got about my question slide. This is, I know, hopefully it doesn't make you puke. That's a Golden Gate Bridge. That's the coast. We went over Alcatraz Island a minute ago, where we went past it. I think this will loop. So there's the Golden Gate Bridge. Now we're going back out the bridge. This was all done, and these data are online. This was all done from a boat with the LiDAR pointed sideways. And we just drove along the coastline and scanned it. So you can see a lot of stratigraphy, and there's a lot of geomorphology that you can see here. Some of it's an artifact of the scanning, but some of it is actually, yeah, I'll stop. Some of it is actually actual geology. But so yes, and you can, if you get 3D point cloud from one source and 3D point cloud from another source, and they're all accurately geo-referenced, you can merge them together and have, we did that with, so what we would do a lot of the time is do a bathymetric survey at the highest possible tide. And so we're shooting up into the intertidal zone, onto shore a little bit, and then come back at the lowest possible tide and do a terrestrial LiDAR survey. And then there's going to be a little bit of overlap between them, hopefully, and merging them is actually really easy. And you get seamless from hilltop to Marine Canyon. Paul. Yeah. OpenTopography.org. Again, it's public domain data. You do have to ask. It's kind of the same as the California Real-Time Network. In fact, it's the same people. It's akin to that in that it's free and available, but you have to ask. They don't just, it's not just click on a website. You have to send them an email and say, and if you have a .edu email address, then they'll give it to you. And it's a way to view publicly available, already processed LiDAR data, elevation data. In fact, Paul sent me a link to the LiDAR data for right out here where we flew the other day before we met. Sharon. Well, I try to put that kind of stuff at the end of my talks, but apparently I haven't. Whoops, I'll stop it. Don't worry. I can work with you offline on that. There are some tutorials. A lot of the time the vendors will have, YouTubes and other, because basically they want people to look at their data and play with it and be impressed by it and buy their systems. So it's in their interest to give you a little bit of instruction on how to manipulate it. If you're talking about learning how to, like, from raw data, how to process it and get to final products, that's not usually available. There's no real resources for that. But if you're a GIS person and you go on, say, Esri's training website to their catalog and you search for LiDAR, there's a lot of tutorials for how to work with LiDAR, already processed LiDAR data inside ArcGIS. So that's a good place to look. Sure. Yes, one more. So I don't know of a system that replaces the RGB camera that's co-located, coaxial with the LiDAR. I don't know of a system that replaces that with, say, a multi-spec or a hyperspec camera. so that you get spectral information for the XYZ points, not just RGB. I guess in theory it's possible, but LiDAR isn't probably the system that's going to give you things like soil composition or chemical properties of something or plant vigor or any of that kind of stuff, except to the extent that that is expressed as a three-dimensional characteristic. So obviously, conifers, pines that have pitch pine cancer disease, they're all spindly and there's not much, foliage on them and they look sickly. And so three-dimensionally, they're going to look a lot different than a healthy pine tree. So you might be able to tell something about that. But in terms of what, say, a hyperspectral camera or a multi-spec camera is going to give you in terms of the ability to measure plant vigor or nutrient content or any of that, this isn't really the system for that. This is a system for creating 3D models and making pictures that fit them, but not so much an analytical tool. I also want to say that bathymetric LiDAR, that is wavelengths of LiDAR that can penetrate the water and give you the bottom of a water body, exist, but not small enough to fit on most, but not on small UAS. They're too big, they take too much energy. They usually use blue or green laser wavelengths because they penetrate through water better. But there isn't a bathymetric LiDAR system that can go on a small drone yet. But terrestrial, it's all good. Yes. I don't know. I can't answer that question intelligently, but I'm sure it's a good one. Yeah, I mean, that was going to be my answer, but it's not based on a full understanding of. Yeah. The question was full. Say it again. Full waveform, right? Right. So it may be available for very large drones. I think the systems are just big. But for small aircraft that we can fly under Part 107, remember that's less than 55 pounds. I don't believe there's a system that does that yet. All good? Well, thank you very much. Day 4, almost in the bag. And I'm happy to talk to anybody about this kind of stuff. I can go on forever. Anytime.